All right, let's start. Welcome to my talk about PTXdist. I'm Roland and I work at Penguin as a systems integrator, and I have been using PTXdist on my daily basis for the last 3 years, I think. Yes, but it's much older than that, as we'll see. So yeah, what is PTXdist? PTXdist is a build system with focus on building embedded Linux images from source. So that means if you run PTXdist, it downloads all the sources from the internet and compiles them and builds them into a nice image, which you can flash onto your devices. And under the hood, we're using proven technology, which you probably already know, like GNU-make for the dependency resolution and Kconfig for having a nice user-friendly menu, and then some bash and AWK code as glue code to couple them together. We are doing monthly releases now, and the first version I could find from PTXdist was from before August 2003, and then the repo was converted into SVN. So yeah, it's already quite old. But there hasn't been a talk for a while, so this has to change now. PTXdist is GPL licensed, as you probably already know this license, yeah. And we're also having a homepage now. Let's have a look at a typical BSP. First, you have this folder structure, which is quite usual. You have some configs in your configs folder. For example, the PTXconfig contains all the software that you want to build in your image. And then we have a platform config that defines the hardware you're using, and the kernel config. Yeah, this is basically the config file for the kernel. And in this case, we're also having a barebox configuration, which configures the bootloader, which we're using in this case. Then we're having some files in the project root directory, for example, an etc fs tab and an etc shadow file, which we want to install on the target. And then we also have some custom rule files for our BSP. Yeah. And the philosophy here is that your BSP looks just like the PTXdist install directory, and you can override and extend the files from PTXdist locally in your BSP just by copying them into your BSP and then adapting them to your needs. Okay, first look. What you will see when you're working with PTXdist are these two menus. As I already said, we're using Kconfig for that. On the left here, we have a menu config for the user space configuration. So there's everything in it. I don't know if you can read it. Probably only the people in the virtual first row can read it. Like shell and console tools, scripting languages, communication utilities, applications, editors, and so on. So this is where you would select the software that you want to have on your target. And on the other hand, you have the platform configuration menu. This is everything bare metal, like configuring the Linux kernel or a device tree compiler and some console options and some bootloaders and the images that you want to build for your hardware. Right. If you're working with embedded Linux, you often have to apply patches to your packages. For example, in this case, we're applying 2 patches to Linux and 1 patch for BusyBox. And as you already see, we can just drop them into these folders in your BSP, and they get picked up automatically by PTXdist during the extract stage. So in this case, the Linux patch tier is in the configs platform v7a folder because it is platform specific, and the BusyBox patch tier is just in the patches folder, so it gets applied for every platform that you want to build, which we'll see later. Yes, you can edit the patch queue. Maybe if you want to develop on your package, and you can just extract the package and then change into the package tier and use Git or quilt to work on your package, and then it will synchronize these patches in these directories. For packages, there are different types of packages. So for example, you want to have some software on the target. This would be a target package, of course, and is built on the host for the target architecture, like, for example, systemd and busybox and core utils and whatever. So you have to use a cross compiler for that. And on the other hand, you need some host packages too, which are compiled on the host and run on the host. For example, in this case, maybe you want to build a vfat image, or something needs to use Python for the build system, or CMake as a build system. And in this case, we would build the respective packages for the host to be independent from the host system. So we can run on, I don't know, year-old Debians and CentOS hosts, and we don't have any problems finding the software that we need. And the third category is image packages, which, is basically defines the image format, like ext or vfat, as I already said, or I don't know. You can always, you can also, for example, build images for Rauk, like software bundles, software update bundles, things like that. And there's a nice wizard in PTXdist for creating new packages, because I think in upstream PTXdist there are about 900 packages prepackaged, but you will probably have some software that you want to use on your target that is not packaged upstream in PTXdist. So you have to do this yourself. And you can just use this PTXdist new package wizard to create a new target package. And it asks you some nice questions like, what is the package name you want to use? What's the version? Where can you download it from? And so on. And in this case, what is the build system? And then it generates you the right files in the rules directory. In this case, the mypackage.make is the make file that contains all the recipes, what you want to do to build your package. And then the .in file is the Kconfig snippet for the menu that gets included in the menu. Let's have a look at the in file first. This is standard Kconfig language. In this case, we're first defining the section for PTXdist so it knows where to include it. In this case, it's project specific, but you could also have one of the categories that I was talking about, that I was showing on the previous slide, for example, editors or communication utilities. Then you define your config symbol. It is usually the same name of the package in uppercase. It is a tri-state option, so you can select yes, no, or as a module. We'll see about that later. And then you have to select your dependencies. In this case, we need to use the CMake host tool because we're using CMake as a build system. So PTXdist needs to build this one first before building my package. And then also we're selecting libusb as a dependency. And then some prompt and help text. Then there's the mypackage.make. It starts with a list of definitions as variables. So for example, here the version, the package name, where you can download it, and also this MD5 sum, because when you download things from the internet, you really want to make sure that they are the right things and there hasn't been any corruption. These are mostly standard and you don't have to change them, except of course for the MD5 sum and the version. And you can just use them as generated by the wizard. And the make file also then afterwards contains the stages that you built your package with. Every package starts with a get stage, which is not shown here because we can just use the default get stage in PTXdist. And You can always let it out if you don't need it, if you use the default one, but you can always define it if you want, and it gets picked up by PTXdist. So in the get stage, you would tell PTXdist how to download the image from the tarball from the internet. Then it gets extracted in the next stage, which is the extract stage, which is also not shown here because it is also the default stage. Yeah, it basically extracts the tarball into the build directory of the package. Then the prepare stage is partly defined here because we have to tell PTXdist to use CMake to build our package and use these config options for CMake. So for example, you can define here CMake in this case, or just also use auto tools, or if you're building a Python package, just use the Python build system, and everything else for these build systems, at least PTXdist knows how to build. And also, if you don't have a prepare system, you don't need a prepare stage or something, you can just set this to no, and then PTXdist will just do nothing. After preparing the package, it is compiled. This is also not shown here because we just need to call make, basically, in this case. And after compiling it, it gets installed in the install stage. So PTXdist under the hood installs the package into a directory just using the default install rule from the make stage, from the make file from the package. But we mostly don't want to install everything on the target which the package installs. So, for example, maybe the package installs documentation or example configurations or stuff you just don't need on the target. So the next stage is the target install stage, in which we define first the variables for our OPG package, which gets built by PTXdist, and then we just cherry pick the files that we need from the file's install location and tell PTXdist to throw this into our package. And this way you can just cherry pick all the files that you need on the target. Right. I think that's everything for this stage. Let's have a look at another feature, which is layers. There are a lot of layer mechanisms in PTXdist, and layers are really, really useful if you want to customize software. For example, in PTXdist, we have alternative config files. So this is just about customizing one config file or a few config files for a package without having to copy the package rules, adapting the package rules to your BSP. And in this case, you only have to copy the single config file and adapt it. Then there are platforms. As I already mentioned, platforms are about different hardware which you want to run your BSP on. Then there are software collections, which defines different sets of software. For example, if you have different product lines which are quite similar but not the same, you can define a different collection for each of them and just use the one collection for the one product and the other collection for the other product. Then there are Kconfig Diffs. Maybe if you want to have similar kernels or something, you would just need to maintain a diff between them. And then there are base layers, which are basically the most pure form of layers, I think. And you can basically do anything you want with them. All right, let's have a look at alternative config files first. Here we have a snippet from the upstream rule for cups from PTXdist. And in the target install stage, it uses this install alternative macro to search for etc printcap. And if PTXdist sees this macro, it searches in different locations for etc printcap, for example, in my BSP project root, so in my own BSP first, then in the config folder project root, in the platform folder project root, then in PTXdist itself. And if it still isn't found, it will go into the cups install dir and the cups build dir and search for etc printcap. And this way it uses the first etc printcap it is found at the first location it is found. And usually PTXdist includes a default version of these config files, and you can overwrite them in your BSP. That's easy. Let's have a look at platforms. As I already said, platforms are all about different hardware. So in this case, we're having a platform Raspberry Pi, and it uses the ARM1136JFS cross-compiler and a kernel 4.19, and it builds an HD image, and the Raspberry Pi also needs a boot partition, which is vfat. But we don't want to use only the RPI. We also want to use other platforms. For example, here we have a generic v7a platform for ARM v7a, and we're using the kernel 589 in that. I think it's the current, at the time of recording, newest kernel. And we're also using Barebox as a bootloader and also the HD image. And then we have a v8a platform for 64-bit ARM. And we're using an RC kernel here and also the Barebox and an HD image. So this way you can develop 4 different platforms at the same time using the same Userland software. So for example, here systemd, busybox, and cups. And you would then select the platform you want to build before building all your images. And all the configuration contains the same software, but different kernels and different bootloaders. Then there are collections. This is all about different software configurations on the target. For example, if you want to have GDB and strace and stress-ng for debugging, you could have a debug collection, and then you would need to set these packages to M. This is the tri-state value, as I mentioned before. Then you would, in your debug collection, set them to yes, so they are built into the image. And in another release collection, you would just disable them so they don't get built into the image for release. So there are different scenarios here. As I already said, you can select them before building your image. So you would just use PTXdist collection to the path to the collection config and then build your image. Or the image that you build can also use the collection by using this packages variable here. And then the image will use the software from the collection. And in the second scenario, every image that doesn't explicitly use a selected collection just uses the collection you selected with this PTXdist command. Right, next feature, Kconfig Diffs. The use case here is you're having a different kernel, but you want to have a similar config, but not the same config. For example, you are using a debug kernel package to develop your kernel or to develop your BSP in general. And you don't want to roll out all these debug config options to your release. So you're having a different kernel package in. And then you can set in your kernel package these ref config to the config from your release kernel, and the other line here, underscore config, tells PTXdist which config to use for the debug kernel itself. So then you would go and configure your debug kernel package, and in this step, PTXdist already uses the refconfig from the release kernel version and predefines everything in the menu that is like in the release kernel. But if you select different options, it afterwards writes the diff between the release kernel config and the debug kernel config into this .diff file. And the .diff file in this case only contains two symbols, like, for example, DMA AP debugging. And the first line is always the MD5 sum of the reference config. So in this case, the release config. So you can always, PTXdist always knows that when the release config has changed, it needs to recalculate the debug config from the diff. So this has the implication that every time you're updating the release config, you also have to update the debug config, but this is just another PTXdist command. So you just tell PTXdist old config kernel debug, sorry. And yeah, it's basically 1 second or so. But it has the advantage that you're solving any merge conflicts that would occur during the update at an earlier time. So, for example, if you deferring this this update to a later stage, for example, you only have a config snippet and apply them regardless on what the release config is, then it could lead to merge conflicts during the build. And maybe the person that's building the BSP is not the person who is developing for it, and then someone doesn't know how to solve these conflicts, and leads to confusion. So in our case here in PTXdist, we're opting to solve these conflicts early. This Kconfig diff mechanism is also used for base layers. And in base layers, all you need is basically this symlink named base. It can also be a Git submodule or just a directory or something else. It just needs to be named base. And it points or contains the base layer that you want to build on. For example, here we have finished BSP named DistroKit, and it contains a v7a platform with a kernel config and a platform config and a PTXdist config and some rules, and we want to build on this image. For example, because we want to enhance our product line and add another product without changing the original product. In this case, you would just create a new BSP, set the base symlink, in this case, to DistroKit, and this is basically all you need. And if you now go into the menu config, then PTXdist searches for the first PTX config it finds, and it will go into this base layer because it doesn't find it. If this one doesn't exist, it wouldn't find it, but the base layer has a PTXdist config. So it uses this one. Then when you change something in the menu, the diff is calculated in the current layer, which you are currently using. So in this case, the diff is between this base layer config and this config in the current layer. And for example, if your current layer also contains another package, then PTXdist will find it when you're using this layer, but it will also find any rules that you have in the base layer. So there are some caveats. As we already saw in the previous section, this .diff, Kconfig diff, contains the MD5 sum. And I already explained this. So yeah, they are pinned down via MD5, and you can run old config to synchronize these diffs, and it has the implication that you solve the update conflicts early. And PTXdist is always used as the lowest layer implicitly. So, for example, this DistroKit layer doesn't have a base link, But in this case, PTXdist would just use its own install directory as the base layer. Okay, there are some more features in PTXdist which are not about layering, but which are useful nevertheless. For example, we have code signing infrastructure. And the use case here is verify boot or high assurance boot. For example, the IMX6 processors, or I think 8 and 7 also have this feature. They contain some code in the ROM, which you can use to pin down some fingerprints or certificates to sign your bootloader. So every time the ROM coder is loading the bootloader, then it would first verify this bootloader. So if someone else wants to verify this bootloader, then the verification would the signature would not be the same, and the ROM coder would not load the bootloader. And then in the next step, the bootloader loads the kernel fit image and verifies a signature, and then the kernel would use the signed file system. And on this step, maybe you can use, there are certain applications like OBFS authentication or EMA-E4M or something. But the important part, which I want to stress here, is that it is a chain of signatures. So everything from the ROM code on, and the ROM code you cannot change, and from the ROM code on, then everything is verified. And the other use case is you want to sign your update bundles. For example, I think Rauk can do this if you want to use it. So you can download your update bundles from the web and make sure that they really contain the right software released by the right person. And maybe you want to also have some key set for development and some key set for the release phase. So you would you can configure your hardware in the development phase to only trust your development keys or your development signatures, and you want to make sure that the development images are not used for the release phase. And for example, in the development phase, you can also use something like soft HSM, which is easy to use, and in the release phase, you can then use maybe a hardware security module, a really hardware security module, or a cloud signature service. And PTXdist splits this in two steps. We have providers and consumers. And the providers are really about talking to the HSM. And I don't know, in the case of soft HSM, select the right keys from the right locations in your BSP, or in the case of NitroKey, prompt you to insert a NitroKey, something like this. And you can select different providers in the platform config menu. For example, you have a provider for your development keys and a provider for your release keys. And we also have a package wizard for doing your own code signing provider. And on the other hand, we have these consumers below here. And it's basically, they use the abstraction in PTXdist to select the correct keys, or select the right key material to sign their images, or their images basically. Recent PTXdists also have some nice features to get to know your BSP and debug it. For example, we have a BSP Info command, which lists everything you need to know about your BSP, where it is located, where the PTXdist is located, which platform config, which PTX config you're using, which images you're building, and so on. And we also have the same for single packages. For example, here BusyBox. is at version 1.31.1. It has a GPL license. The source is located here, and its download URL, and where the patch folder is located, and the rule file and the menu file. And you can use this to debug the internals of PTXdist if you want, or if you're not sure which on which layer the package comes from, you can find this out. Yeah, you already saw these license variables here, and I'll quickly talk about this. Every package can have these _license variable and _license files. In this case, we are setting them to 0BSD, and this really means that you're defining the project license for the package itself. So PTXdist knows that this package is available under the 0BSD license, and it also knows that the license is contained in the folder license in the package's build directory, and the MD5 sum of this file is the following. So we are also pinning down the MD5 sum here, so we get notified by PTXdist if this license changes. And in the next step, you can use this to build a license report for your BSP. You would basically just call PTXdist make license report, and then it collects all these license material from the available and selected packages and drops them into a nice PDF. So you will see here DOSFS tools, E2FS procs, GDB server, glibc, and the copying files for all of them. Yeah, and they also contain this this dependency graph, so you know the open SSH, which is licensed under BSD and BSD3 clause and MIT and BeAware and ISC license. It depends on the zlib, which is licensed under the zlib license, and OpenSSL, which is licensed under the OpenSSL license. So you can find software that maybe depends on GPL v3 if you don't like GPL v3 or something. Yeah. You can also use this as a template for your license compliance process. All right. Next topic, reproducible builds. PTXdist tries to build packages reproducibly by default. You can select which date it uses, and the goal here is if you have the same source input, then you also have the same binary output after compilation. So you always know if you're having the same binary on two build hosts, then it has to come from the same source. And PTXdist does this by setting this source date epoch variable during build, and the package's build system has to respect this, but I think it's quite standard now. There are only, I think it is quite established right now. And of course, the date is only one thing we can pin down, but there are various different variables that go into the packages, and which the packages itself have to make sure to use reproducibly. And this is really an ongoing effort, but PTXdist does everything it can. Next, we're also having a mechanism for your BSP to document itself. And in this case, you have a doc folder inside your BSP, in this case DistroKit, and it contains some restructured text files, and PTXdist is then using strings to build a nice, in this case, HTML documentation, or it can also use PDF as an output format. Then there are some development helpers, which are really useful if you develop with your BSP. For example, if you want to develop your application, and when developing your application, you need some some container to run it in, right? So PTXdist in this case has, for example, an NFS root support. And if you call this NFS root command, then it first builds all the packages, of course, and then exports the sysroot folder where all these packages are installed. On the devil host, it exports this via NFS and sets the correct access rights too. So you can just tell your kernel to use this NFS root command line. And if your board has network, then it will just use this as this exported NFS folder as the root file system. And this has the advantage that you can use Vim on your development host and don't need to SSH to the target and use the, I don't know if you have Vim on the target, but yeah, it's mostly not a fun experience. And you don't also need to reflash or rebuild or reboot your target. So you can just edit files and plates. For example, if you just want to test a config change or yeah, something like that. The next thing is we also have a GDB wrapper. You can use this with a GDB server or just to debug core dumps from your target. And you can just use GDB on the host with this PTXdist GDB command. And it's basically just a simple wrapper that sets up the right sysroot. So GDB finds all the debug files, debug symbols, and yeah, something like that. Also quite nice to have. Yeah, as a summary, what is PTXdist? What makes it unique? It has a quite useful menu interface. It has, under the hood, it's using stable and known technology. The focus is on reproducibility, so we pin down most variables which we can control as much as possible. So if someone else is building the same BSP, then we hope it's the same output as someone else is building it. And we also like to solve conflicts early rather than later. We have nice code signing infrastructure and some development helpers which help you developing your application. If you want to try it out, you can have a look at DistroKit, which is a pre-configured BSP for a variety of dev boards. I think at least Raspberry Pi 1, 2, and 3, then some older development boards like the Nitrogen 6 boards. We also have a QEMU emulation for ARM vExpress, and also I think for some MIPS platform and x86 64-bit. And I think we're also having some 64 ARM v8. Yeah. So yeah, you can use it to try PTXdist, or maybe just use it to build a BSP for your own development board. Yeah, have a look at this homepage here. Here are the references. The icons are from Font Awesome, and the Tux logo is by Larry Ewing and the GIMP. Right, that's the end. Thanks for listening, and time for questions.